So another example, points and polygons. Here we have a land use polygon data set and individual point locations for schools. So we can put those two together using the overlay process, and we know then what zone or what land use code, what zoning applies to each school location. So the way this works is essentially what we're doing is we're creating a spatial join between the tables. We're joining them based upon their spatial attributes, rather than what we would do with a table. With a table join, you're matching those primary keys and foreign keys in the table that have to be the same. Well, a spatial join like this overlay, just forces the data together. In this case, it's forcing the polygon data into a new output table and a new output feature class that will be a point feature class containing information from both the parent point data set and the polygon that was overlaid onto it. The line and polygon overlay works by, you guessed it, assigning polygon attributes to the lines. So in this case, a stream network over a polygon data set of geological units. Then we can associate the information from the geological units with each stretch of a river, or each segment of a line, if you think of it that way. And so here, one example we might use this for would be using the rock types to help model infiltration rates. So if we know what the rock type is, we have an idea on how much loss we might experience from the stream flowing across the rock, and how much the water will infiltrate that rock surface and descend, percolate down into the earth beneath it. So that same example, each stream in the network, the line network, acquires the information from the specific geological unit within the polygon that describes the geological unit. Streams are split at the unit boundaries, just like roads were split at land use boundaries between different land use categories for the urban example. So it's doing that exact same thing. And so the advice that I would give you when doing these, that you may have noticed Price is doing in her examples, is when you create a map overlay, that the name of the new data set ideally should be something that makes sense. If you have nothing else to use, rely on combining the two and put the name of the overlay first and the name of the other information second. And so here we've got the stream information first in the file name, and then the indication that it's coming from the geology as the second part. So we overlaid streams over the geology data set. We know by looking at the name that that's what happened, and then we have some idea about the history of the creation of that data set when we come back to it in the future when we've forgotten what we've done. So a real brief review before the last of the overlay processes. What we're doing in overlays is we're combining features from vector data sets spatially, and we're producing all possible new feature combinations that exist between the two data sets. If we combine polygon and point data, we're going to get point data out. If we combine polygon and line data, we're going to get line data out. If we combine polygon and polygon, we're going to get polygons out. And the output will be a new data set, a new feature class or shapefile that contains all of the selected attributes from all the different possible combinations of the inputs. So with polygon on polygon overlays, here we're combining geology and slope class what we wind up with is all possible combinations of those things together, and the table will then be will share information from both inputs and be broken up in such a way that we can analyze individual polygon characteristics that combine, in this case, the geological stuff, so the rock type, with the slope class, how steep is the slope. So we'll know in the table and visually by looking at it just those things. If we're familiar with the data set, we'll know what geological unit is, maybe what rock type it is, how old the rocks are, things like that, and then how steep the terrain is by knowing what the symbols for the slope class mean. And the table will contain all the information from both those. So here's a great little slide that shows kind of what's happening underneath it. We've got the geology information, got the slope information. We spatially combine those things. And in the little diagram on the right, then you see the complexity of the geometry. Okay, that may be a little bit more difficult to see on the previous slide, but here we're combining all of these different polygon outlines together, and we're forcing into existence basically all these little slivers that are things that we might have wanted to avoid if we were digitizing. But here we want these because each of those little polygons is a different combination of features from the geology input data set and the slope class input data set. And so we're winding up with inherently a more complex data set, but it carries the information forward from both of those inputs, and so it becomes something that's a little bit more powerful in some ways for analysis, and easier in some cases to find out which specific piece of or parcel out there, or enumeration unit, or whatever you want to think about it, whatever these little polygons are, we know a lot more about them from a single data set. So what are the actual functions in ArcGIS that perform overlays? We have intersect and union, intersections and unions. An intersect function will combine and keep all of the common features between the two input data sets. Those can be points, lines, or polygons, and it will keep the lesser of the input types. So, for example, if you combine intersect lines with polygons, you're going to get lines out of it. If you intersect points with polygons, you're going to get points out of it. If you intersect points and lines, you're going to get points out of it. You're going to get the minimal intersection between those things as your output. Union only applies to polygons, then it keeps everything. Okay, intersect only keeps the common features between the inputs, but a union keeps all possible combinations of all the input. So intersect, keeping common areas. Union keeps everything. Okay, so the purple in this diagram in the upper right is the result of the intersection. It's the common areas between them, and the union on the bottom is keeping everything. And an example of union that we've seen before, now we know the name for it, combining a geology data set and a slope class data set, then we get a result that contains all of the information from both of those. They were both polygons, and now we can do things, slightly different kinds of analysis, visually and also based on the table, perhaps a little bit more easily since they're combined. Intersection here, an example of why we might want to do this. If we have two different spatial geometries for very different environmental and human demographic information, residential areas is a polygon, and something known as the Opeche Formation, which is a rock formation, a geological unit, happens to be associated with radioactive materials, rocks that produce radon gas. So if we know that we've got a natural hazard, being a rock formation, a rock type that is known to emit and produce radon gas, which is toxic for humans, and we have residential areas, we might be interested in knowing, are there any spatial relationships between those two? So if we were to buy a house, are we likely to buy a house that is radon free, or is it one that may be susceptible to radon infiltration? And so the intersection gives us an idea about that. So what we're seeing in the resulting data set is the intersection between residential areas and the Opechee Formation, shown in purple. So those areas, or the zone within the residential areas that's purple, is if you have a house on top of that, you might be more susceptible to having, or more likely to have, radon gas in your basement. So here's just another example of the same thing, slightly different scale, zoomed out a little bit, looking at the residential areas, the Opechee Formation, where the intersection occurs. So you can see, I hope from this, if we have different data sets and we're interested in knowing the relationship between them, because we're investigating something like the presence or potential presence of a toxic material or anything else. It doesn't have to be anything nefarious and horrible like that. It can be something a lot more innocuous. But we can put these pieces of information together and get something that clues us in. It helps us focus, perhaps, our ultimate project, as if we're interested in maybe notifying people in residential areas about the potential of radon gas, then we could use this information here to help inform our efforts, and we won't send postcards necessarily to every single address in this residential area. But if we then combine this information with which houses actually exist in the residential areas, then we know we have a smaller list of addresses that we'd have to target to get information out to them, assuming that's what we're doing this for in the first place, is to try to a public health information campaign. So hopefully that makes sense. You know, this is what we're doing is narrowing down space based upon characteristics that we know are attributes of these different spatial categories, and we can combine them spatially using the overlay tools. So another example might be, here's a fairly common one, as we're interested in looking at the habitat for different plants and animals or other organisms. We can use a series of spatial queries and spatial functions, overlays, and whatever to help us narrow down and isolate where that potential habitat is. So if we know we've got a snail species, for example, and we know that the snail species is associated with a particular elevation range where it tends to be found, we know that it preferentially seeks out areas that are high in calcium, so limestone rock formations, and if it prefers shade, and particularly shade under certain kinds of trees like conifer, evergreen trees, and it prefers a lot of shade, then we look for dense conifer distributions. So we can combine those things together using spatial techniques, and we wind up with the result over there. Here's where we're likely to find snails. These are 3 conditions that we know for the snail, and those polygons meet those conditions, so we've modeled potential snail habitat. So remember, when you're doing map overlays, how it works when you're doing the intersections. When we're intersecting polygons together, You can choose to output either polygons, lines where they intersect, or the points of intersection from those. The default's going to be completely putting out all information in polygons. But the output dimension for intersections for the other types, when you combine anything else, has got to be the same as the input, or same as the lowest level of input. So if you're intersecting lines, for example, you can choose to intersect out lines or point data sets. If you're intersecting points with lines, you're only going to get points out. If you're intersecting lines with polygons, you're only going to get lines out. If you intersect points with polygons, you're only going to get points out. Okay, so remember that. That's a really critical characteristic of intersect versus union, where union keeps everything, all possible combinations of the input polygon data sets. So here again, sorry, I'm doing it again, the intersecting different geometries. If we're intersecting polygons and lines, you can choose to output either lines or points. Those are both valid outputs intersecting the polygon. Intersecting points with anything else is always going to give you points. So again, that's a really critical aspect of the intersection function with vector data sets. So if we think about the extraction functions from before, they're essentially map overlays, and we add to them the ones we've just discussed. So clip, erase, intersect, and union. Graphically, what are we doing? When we clip, we're basically getting a cookie. We're using the overlay data set on top of the input data set. We get out the cookie. With erase, the overlay data set punches out and erases that area within the input. So your output is missing the cookie cutter. When we do an intersection, we're getting all of the common information between the inputs. In this case, they're both polygon inputs, so we get the intersection of the polygons at the smallest of the polygon inputs. The one that covers the least amount of area is going to be what we get out, and we're going to get all of the data from the input and the overlay data sets with that. The union is when we combine both and we get all of those at the maximum size of the inputs. So each of these is they produce output data sets that are some combination of information from the input and overlay. Remember or jot down in your notes somewhere, or note the page numbers that describe these things in your textbooks, what these different functions are doing, and think about how you might use them to your advantage in analysis when you need to get certain characteristics about study areas through the different stages of your analysis. So here's this idea of slivers again. Slivers, in this case, are going to be teeny tiny little polygons that are created during our geoprocessing functions. And they come about as we have slight differences in boundaries between the input polygons, for example, here. And if we do many different kinds of geoprocessing, pulling together lots of different data sets, we could wind up with quite a few of these little slivers, and they're tiny little areas, and they may not even be significant. They may not be the right size to be significant for our project, for our study. So then they become a problem, and you may or may not want to keep those little slivers. They may be important for some studies, but in a lot, they may be something you just would rather get rid of.